10.5 Lesson 2 Area of a Polar Region. Our objective for today is you'll be able to write a definite integral to find the area of a region bounded by a polar curve and two radial lines. Vocabulary: radial line. Yesterday we derived Theorem 10.13, area in polar coordinates. And if you have a polar function f, and it is continuous and non-negative on the interval from alpha to beta. It could also be non-positive, but remember, the formula is not necessarily valid if f takes on both positive and negative values on the interval from alpha to beta. And this particular restriction, as we said yesterday, is just to make sure that you're not doing more than one complete revolution. Then the area of the region bounded by the graph of the polar equation and the radial lines alpha and beta is given by this definite integral. Area is equal to 1/2 times the definite integral from alpha to beta of the square of the polar equation integrated with respect to theta. And of course, yesterday we saw that this integration formula was derived starting with the pre-calculus formula for the area of a sector of a circle, which we used as our representative element to approximate the area of our polar region, and then we wrote a Riemann sum and took the limit of the Riemann sum as the norm of the partition approached 0 to get this integration formula. So now we look at example 1, finding the area of a polar region. Find the area of one petal of the rose curve given by r is equal to 3 times cosine of 3 theta. The first thing that you need to do is you need to look at this. This is going to help you tremendously. So you can look at the graph of your polar equation, and the instructions are to find the area of one petal of the rose curve given by r is equal to 3 times cosine of 3 theta. It doesn't really tell you what the limits of integration are, but it does tell you that you want to find the area of one petal of the rose curve given by the graph of this polar equation. So you have to look at the graph, identify one petal of the rose curve, and then determine what the limits of integration should be. So here we have the graph of our polar equation giving us a rose curve with 3 petals. And it's only asking us to find the area of one of those petals. So it says here, the area of one petal of the rose curve that lies between the radial lines theta is equal to negative pi over 6, and positive pi over 6 is 3 pi over 4. This is, of course, the answer to the problem, and we'll look at how we get that. But we need to begin by thinking about why these are the correct limits of integration. And that begins with, first of all, looking at the graph and making the visual observation that a petal starts at the pole and it also ends at the pole. So if you want to figure out what theta is for each time the rose curve is at the pole, you will begin by taking the polar equation and setting r equal to 0 and solving for theta to determine the values of theta for which the curve will be at the pole. That's the first step that you need to do. Look at the graph, make the visual observation that each petal of the curve starts at the pole and ends at the pole. So set r equal to 0 in your polar equation and solve for theta to determine the values of theta that will give you points at the pole for the curve. So we set r equal to 0. We divide both sides of our equation by 3. So on the left side we have 0, and on the right side we have cosine of 3 theta. You cannot divide both sides of the equation by 3 here because you are taking cosine of 3 theta. You're not multiplying cosine by 3, you're taking cosine of 3 theta. So what you have to do is you have to use trigonometry to solve this trig equation. So you can go back to the unit circle and help you solve this trig equation. Cosine of an angle theta is the x-coordinate of the corresponding point on the unit circle. So here we want to look for angles 3 theta whose cosine values are 0. So cosine values are 0 when the angle is either pi over 2 or 3 pi over 2. But in our problem, the angle is represented by 3 theta. So cosine of 3 theta will be equal to 0 when 3 theta is either pi over 2 or 3 pi over 2 or any of their coterminal angles. So pi over 2 plus pi will give us 3 pi over 2. And if you add pi to 3 pi over 2, you'll get 5 pi over 2, which is coterminal with pi over 2. And if you keep adding integral factors of pi to pi over 2, you'll get all of the values that 3 theta could be, so that cosine will be equal to 0. But you need to solve for theta, not 3 theta. But this is the step that you have to take first. Now you multiply both sides of this equation by 1/3, and you get theta is equal to pi over 6. When you multiply pi over 2 by 1/3, you get pi over 6 plus pi over 3n, where n is an integer. And now you can choose certain values for n. So for example, this particular rose curve, if you start at theta is equal to 0. Suppose you evaluate your polar equation when theta is equal to 0, what will you get for r? So you will have 3 times cosine of 3 times theta. 3 times 0 is 0. Cosine of 0 is 1. 3 times 1 is 3. So you'll get r is equal to 3 when theta is equal to 0. So that tells you that if you start at theta is equal to 0, you're actually starting at this point on the rose curve with polar coordinates r theta, where r is equal to 3 and theta is equal to 0. And then as you go from theta is equal to 0 to theta is equal to pi over 6, this part of the curve is being traced. So how do you get the other part of the curve that is down here? You will get that by choosing a value for theta that corresponds to a negative angle of rotation. If you rotate clockwise from the polar axis, you'll have an angle of rotation that's equal to theta is equal to negative pi over 6 radians. And in fact, you will get negative pi over 6 from this set of possible solutions to our equation by setting n equal to negative 1. Because remember, n is any integer. So you will have pi over 6 plus negative 1 times pi over 3 would be negative pi over 3. And when you add the two fractions, you will have pi over 6 plus, multiply this one by 2 over 2 to get negative 2 pi over 6, which will give you, add the numerators, pi plus negative 2 pi is negative 1 pi over 6. And if you let n be equal to 0, then you'll have pi over 6 plus 0, which will give you pi over 6. So those are sufficient for our purposes, which is to find the limits of integration that we need that correspond to the radial lines theta is equal to negative pi over 6, which is shown here. This is the radial line theta is equal to negative pi over 6. And the radial line theta is equal to positive pi over 6, which is shown here. So our region, which is one petal of our rose curve, is defined by these two radial lines and the polar curve that I am now tracing in green. So when I sketch the polar equation from theta is equal to negative pi over 6 to theta is equal to positive pi over 6, I will get one petal of the rose curve. And for that reason, I need to have my limits of integration be negative pi over 6 to positive pi over 6. There are other possibilities that you could choose for what the limits of integration should be. For example, you could choose it so that it goes from positive pi over 6 to pi over 2. And the reason I can get that is by I go back to this equation here, and if I let n be equal to 1, I will have pi over 6 plus pi over 3, or 2 pi over 6, which gives me pi over 2. So if you could also alternatively have the radial lines theta is equal to pi over 6, which would be this one here that I'm now retracing in gold, and theta is equal to pi over 2, which I am now going to trace in blue. You'll notice that on the interval from pi over 6 to pi over 2, the values of our polar equation are non-positive. They're entirely non-positive, or they're entirely non-positive. And therefore, you're looking at this particular petal of the rose curve. But all of these three petals are in fact congruent. So finding the area of any one of them will be sufficient. So you do have other options for limits of integration. For example, pi over 6 to pi over 2, or even from pi over 2 to pi over 6, which will give you the other petal that is over here that I just traced out in blue. And I will also show you this on Desmos, and then we will take a look at setting up the definite integral with the proper limits of integration and evaluating it to complete our example. So if you click the suggested link, that would have taken you to the Desmos version of what we just saw with the graph. So here is our integration formula for finding the area of a polar region. And we now know that our limits of integration, one possibility would be from negative pi over 6 to positive pi over 6. And we have, of course, from the integration formula, the factor of 1/2. And what do we need to do? We just need to take our polar equation and square it. That's our integrand. And that is from the integration formula, and we're integrating with respect to theta. So how do you actually evaluate this definite integral? Let's take a look at the steps that are shown in the example. Before we do that, if you're looking at this is just to make sure that you're not doing more than one revolution on this interval for theta. And of course we're not. We're just going from negative pi over 6 to theta is equal to positive pi over 6. And on this interval of theta values, the values from our polar equation are non-negative. So now we just have to do the integration. So the first thing that you want to do is you want to go ahead and square the polar equation. So you have 3 times cosine of 3 theta, and you're squaring that. So you can distribute the exponent to the 3 and then to the cosine. So that would leave you with 3 squared, which is 9. And you can see that we factored out the 9, so that now it is outside, giving us 9 times 1/2, which is 9 over 2. And then in the integrand, we would have cosine squared 3 theta. So if I want to write an intermediate step here, I would write 1/2 times the definite integral from negative pi over 6 to positive pi over 6. I get 9 times cosine squared 3 theta d theta. And when you factor out the 9, then you get 9 over 2 times the definite integral from negative pi over 6 to positive pi over 6 of cosine squared 3 theta. So the next question you might have is, how do we go from cosine squared 3 theta to what we have here? We do that by using a trig identity, specifically a power reducing formula. Because when you have the integrand written as cosine squared 3 theta, you cannot find an antiderivative unless you do something to the integrand. And what we're going to do is a manipulation by using, actually it's a substitution. We're going to substitute for cosine squared 3 theta with an equivalent expression by using a trig identity, in our case a power reducing formula. So the power reducing formula will allow us to make a substitution for cosine squared 3 theta, which is in our integrand, which we don't know how to integrate. But when we rewrite it by using the power reducing formula for cosine squared u, we will get what? Remember, whatever this angle is, that is u. So when you rewrite cosine squared u, you will have 1 plus cosine of twice the angle that you had, all of that over 2. So this will be rewritten as 1 plus cosine of 2 times 3 theta is 6 theta, all over 2. And that's why you have this particular line. The next step that you want to do is recognize that you have a factor of 2 in the denominator, which you can consider as 1/2 times 1 plus cosine of 6 theta. And you can factor out the 1/2, and when you do that, you will get the following. You will get 9 over 4 times the definite integral from negative pi over 6 to positive pi over 6 of 1 plus cosine of 6 theta d theta. And now you're ready to go ahead and integrate. You're going to find an antiderivative of the integrand and evaluate the antiderivative at the upper and lower limits of integration and subtract. That is, of course, what we call using the fundamental theorem of calculus. So now when you integrate, you're going to integrate term by term. The antiderivative of 1 with respect to theta is theta. The antiderivative of cosine is sine, but you have cosine of 6 theta, so you need sine of 6 theta, but you need to divide by 6, because if you just have sine of 6 theta, when you find the derivative of sine of 6 theta, you will actually get 6 times cosine of 6 theta because of the chain rule, but you don't want 6 times cosine of 6 theta. You want 1 times cosine of 6 theta, so you have to compensate by dividing by 6. And now you're going to evaluate your antiderivative at the upper and lower limits of integration. So what do we have? Well, we will have the next line, but I'll show you like the steps, the intermediate steps that are not shown here. So we're going to substitute pi over 6 in place of theta. So we have pi over 6 plus sine of 6 times theta. So 6 times pi over 6 is pi, all of that over 6, minus, so we're going to substitute negative pi over 6 for theta, which will be negative pi over 6, plus sine of 6 times negative pi over 6, which is negative pi over 6. And of course, we know that sine of pi, sine of an angle theta, is the y-coordinate of the corresponding point on the unit circle, and sine of pi is 0. Sine of negative pi is also 0. So that gives you 9 over 4 times pi over 6 plus 0 minus negative pi over 6, which is plus pi over 6, plus, and this is of course 0, so you don't need to worry about that. So that gives you this particular line here. Pi over 6 plus pi over 6 is 2 pi over 6, or 2 pi over 6 reduces to pi over 3. So when you multiply the two fractions, you get 9 pi over 12, and you can reduce that to 3 pi over 4, giving you the final answer. So what is the area of one petal of the rose curve given by this polar equation? It is 3 pi over 4 square units. So this is actually a problem that you'll be asked to do for your homework tonight, and we'll go ahead and do this one together. So write an integral that represents the area of the shaded region. So you need to begin by looking at the graph. So you can use Desmos to go ahead and graph this polar equation. For this particular problem, a graph is given. So you can look at the given graph. This is from your textbook. And you can see that the shaded region is over here in blue. And the first thing that you need to do is you need to determine what the limits of integration should be. There's no mystery about what the integrand should be. You just take your polar equation and you square it. So the important thing is to find the limits of integration. And finding the limits of integration starts by looking at the graph and making the visual observation that it seems like this particular region, you can see that it includes the pole. So we would think that this particular region is traced from pole to pole. So we need to verify that somehow. But if we start at theta is equal to 0, what would r be? So let's go ahead and just calculate that. So if you have theta is equal to 0, you will get that r is also equal to 0. So in fact, when theta is equal to 0, you do get a point at the pole, and it would be over here. What happens when theta is equal to pi over 2? Then you'll have cosine of 2 times pi over 2. 2 times pi over 2 is pi. Cosine of pi is negative 1. 1 minus negative 1 is 2. So you would get the point with polar coordinates 2 pi over 2, which is in fact the point here that I'm showing in red. So what's going on is the region is traced from theta is equal to 0, and it seems like it's going from theta is equal to 0 to theta is equal to pi. So I believe that the radial lines are going to be theta is equal to 0, or let me go ahead and write alpha. Alpha would be equal to 0, and the radial line beta is equal to pi, which would be over here. Let me go ahead and sketch that in blue. Now if you want to verify that by setting your polar equation equal to 0 and solving for r, you can certainly do that. So you can also set r equal to 0 and solve for theta. So when you add cosine of 2 theta to both sides of the equation, you will get cosine of 2 theta is equal to 1. And using the unit circle, we need to find the angles that would make cosine equal to 1. So cosine of an angle is the x-coordinate of the corresponding point on the circle, and that happens when the angle is 0 or an angle that's coterminal with 0. So you get 2 pi is equal to 0 plus 2 pi n, where n is an integer. So you can simplify. You don't need to write the 0 plus, so you just have 2 pi n, where n is an integer, and you can solve for theta by dividing both sides of the equation by 2, and this is what you would get. And when you make n equal to 0, n is an integer, so you can make n be any integer. When you make n equal to 0, you get theta is equal to 0. When you make n equal to 1, you get theta is equal to pi. When you make n equal to 2, you get theta is equal to 2 pi. So 0 to pi would give you the red part of the curve. And if you go from pi to 2 pi, you'll get the green part of the curve. And it would be this part here. And you could also have your limits of integration from pi to 2 pi, because these two regions are in fact congruent. But that's how you would do it, and you can go ahead and click on the link to watch the same thing that we just went over using Desmos. So if you clicked on that link, you would have seen the same thing that we just went over in Desmos, but your final answer would be the definite integral from theta is equal to 0 to theta is equal to pi, and the integrand would be 1 minus cosine of 2 theta squared d theta. And in this particular problem, we just want to write the integral. But if you wanted to evaluate it, you would have to use FOIL to multiply out the integrand, and then you would have to use a power reducing formula as a part of the integration process. So today we looked at a couple of examples for writing a definite integral to find the area of a region bounded by a polar curve and two radial lines. And our emphasis was on understanding how your polar region is defined, and that will help you to determine what the limits of integration should be.